Alright, so this is the first part of our second set of notes here, so hopefully this will again help out with some of what you're going through, but this section I don't think will be terribly difficult. We will introduce integrals during this section, so that'll be pretty important. So we know how to find velocity when given a position versus time graph, right? We know for a position versus time graph, just to recap, right, if I give you x versus t, then the velocity is just going to be the slope at any instant in time. Or if you know the function, you can just find the derivative and then use that to help you, right? That's what we looked at in the entire last section. So the focus of this section is going to be the opposite situation. How can we find the position or the displacement if we're given a velocity versus time graph? And if you go back to last year, we actually talked about this a lot, right? If I give you a velocity versus time graph, the key was finding the area underneath the curve. Well, we know how to do that if it's a nice straight line, right? If it's squares and rectangles and triangles and whatnot, we can do that pretty easily. So the question is, how do we do it if it's a function, if it's a curve like this? How do we actually find the exact value? And that's going to be what we look at in this section. So leading into that, again, how are we actually going to do this? Well, we know if the velocity is constant, it's pretty easy, right? So I'm not going to spend a lot of time here, but if we do have a constant velocity, we know that the constant velocity equals delta x over t. But if I actually break up delta x, isn't delta x my change? So it's my final displacement minus my initial. So for instance, if I gave you a constant velocity and I told you started at a specific location and you went for a certain period of time, you could find your final displacement just based on basically if I solve this equation, if I rearrange this equation for the final displacement, I can find that in terms of these three variables. So let's go ahead and do that just so I get it. So I've got my final displacement would be equal to, I'd multiply both sides by t, so it'd be vt plus x sub I. Now the textbook, if you ever look online on the Mastering website, or if you look at the textbook, they usually use s for displacement. It's just kind of what they do. We still see enough where we use x on the equation sheet and everything like that, so I will typically just use x, but they do use s interchangeably. So if you ever see that, don't be thrown off too much by it. But anyway, so if it's a constant velocity, I could just use that equation. I would just need to know where I started and then what velocity for how long, and that would be pretty easy to do, right? So what if it's not a constant velocity? What if it's a graph like this where it's a function? Maybe we know the function, maybe we don't, but they give us this velocity versus time function. So I had a typo in here. It shouldn't be position versus time, it should be velocity versus time. But anyway, how could we find the final position based on that? Well, it'd be very similar to what we need to do, right? So if I wanted to find the final position, so if I wanted to find the final location here, I'd need to know what position I started at, right? So we'll talk about that as we go through here. But the important thing, like we talked about last year, is we need to find the area. And one way that we can find the area, and this is something you guys will see in calculus, so I'm not going to delve into it a whole lot, but I'm going to kind of cover the basics. One way that we approach this is what they call basically using Riemann sums or using rectangular small rectangles to find the area underneath that. So what I mean by that is, let's assume that we're choosing a delta t that's very, very small, so it's very close to 0. Okay, so I'm going to choose small widths that are very close to 0. And basically I'm going to build a whole bunch of rectangles that just barely fit underneath that curve. Okay, so if I have a rectangle here that's got a width that's very close to 0, and then I have another rectangle here that's got a width very close to 0, etc., etc., etc. What you're going to notice is, as I continue to add in these rectangles, isn't the area of all of these rectangles going to be pretty close to the total area underneath the curve? Now obviously it's not going to be perfect, right? There's going to be some small little gaps in here where there's some open space, right, that's not covered. But for the most part, I could do this all the way over, and I'm going to get a pretty accurate measurement for the total area underneath this curve. So basically, if I choose a whole bunch of constant velocity steps, so if I was to blow up on this a little bit, if I choose a whole bunch of steps where we've got maybe a constant velocity here, so for a constant velocity I'll just call that c1 for constant 1, and then a width of delta t, and then I've got the next rectangle over, which would be whatever second approximate constant velocity I could work with, times another delta t, and then another one. So again, I'm blowing up this image a little bit to make it clear. But basically what I'm doing is I'm just choosing some of the constant velocities at an instant time, or some of the velocities at an instant time, I'm assuming that it's constant, and then I'm finding the width as a very small interval of t, a very small change in time. And so if I do that, I actually get all of these rectangles, which again, if you look at the total area of all of these rectangles, it adds up to pretty much the area underneath the curve. The reason that's important, so as we look down here, as we start to do that, the reason that's important, and again, they're using s instead of x, but if I find all of those changes, so if I find that constant velocity times delta t, and then the next constant velocity, so v2 times delta t, and I start adding all of these up, and next constant 1 times delta t, etc., etc., right? If I start adding all these up, eventually I'm going to get a whole sum of all of these rectangles. Well, if I'm choosing basically an infinite number of rectangles to fit in there, I'm going to get a very accurate interpretation of the area underneath the curve. And again, you guys will delve into this a lot more in calculus, so I won't spoil all the fun in there, and I'll also keep it fairly basic for us. But what this boils down to is what we refer in calculus as the integral. So again, this is kind of my position function right here. It's very similar to what we wrote up above, where I had x of f equals the initial position plus, originally I had velocity times the change in t. Well, this time I'm finding the sum of all of those velocities times the change of t, as that change in t is very, very small. So I'm finding that sum, which I can replace with this symbol over here, and I know it cut off a little bit down here, but this symbol over here, which represents what, again, they refer to as the integral. Okay, so this would be an integral from ti to t final. So we're going to look at exactly how to deal with this. I know right now this may be a little bit confusing. You will see later on in calculus, hopefully in a couple weeks here, you'll see a little bit more on the integral discussion. The good news for us is the biggest thing we have to be comfortable with is the fact that when they refer to integrals, they're saying that's how we find the area underneath the curve. Okay, so when they refer to integrals, that's how we find the area underneath the curve. So anyway, let's kind of get into that a little bit more. Okay, so let's start by a simple example. Let's start with an example that you guys should be able to do from last year, right? So this is one where we won't have to use any calculus. The figure below shows the velocity versus time graph of a drag racer. We'll call him Craig. Obviously that is completely irrelevant. How far does the racer move during the first 3 seconds? I did throw in here because obviously I just kind of made this graph quickly. The function is supposed to be given by v of t equals 4t. Okay, so this is my velocity function, which means here that this is a graph, basically y equals 4x in other words. But we're using, of course, velocity and time instead of y and x. Okay, so if I want to find the distance, find the displacement, right? How far does the racer go during the first 3 seconds? So I just want to figure out what's the area underneath this curve up to 3 seconds. Well, in order to do that, isn't this just a triangle? Since it's just a straight line function, right? The area underneath this curve, the area bounded by the curve and the x-axis, it's just going to be a triangle. So I just need to know the dimensions on my triangle. Well, we know that it's 3 seconds, so I'm going over 3 seconds. So the only thing I have to do is really figure out my height, and then I'm just going to use area equals 1/2 base times height. Well, in order to figure out the height up here, right, we know that's at a time of 3 seconds. So I just come over here to my equation, my velocity function, and I plug in 3 seconds. Right, so when I plug in 3 seconds, I figure out that that's at a height of 12, and keep in mind this would be meters per second. So then my area is just, again, the area of that triangle. So area is 1/2 base times height. So the base in this case is 3 seconds. The height in this case is 12 meters per second. And I am keeping the units in there, so we notice, right, what happens. If I take 3 seconds times 12 meters per second, the seconds end up canceling out. So I get 3 times 12, which is 36, and then half of that, so I get an area of 18. Okay, so an area of 18 meters, and what that tells me is the drag racer here has gone 18 meters from where he started in the first 3 seconds. Okay, so assuming that he started at a position of 0, he ends at a position of 18. Otherwise, we'd have to pay attention to maybe what position he starts at, but we know that the displacement, the change in displacement, would be 18 meters. So again, this example hopefully sounds pretty familiar, right? If I give you a velocity versus time graph, the moral of the story is to find the displacement, you find the area underneath the curve. So what we're going to see in the next few examples, once we get into it, is the fact that the area under the curve is the integral and we'll see mathematically how we can solve that. Okay, so again, hopefully that first example, not too bad for you. So then example 2, this is another one that we can get through, to be honest, without using any calc. We'll see the calculus side of this towards the end of this section. But let's go ahead and work through this one without any calculus. Okay, so going back to like what we do last semester, last year. The figure below is a velocity versus time graph. Particle does start at 30 meters at a time of 0 seconds. Okay, so keep in mind that's not really reflected on the graph, but we should probably make a note somewhere that the initial position is 30 meters. Right? I'm not starting at 0 like I sometimes do. A. Draw a motion diagram for the particle. Be specific with a labeled axis. So this goes back to a skill that you guys do need to be pretty comfortable with. When we draw motion diagrams, right, they can just be dots, they can be representing the particle. But I'm going to go ahead and give myself then an x-axis here. So somewhere over here I've got the origin, and then somewhere on this side, maybe right about here, I'll put my 30. Okay, so 10, 20, 30, and then 40, 50, etc. I know that for the first second, so my first dot is going to be here. Well, I should say the 0th second, right? Starting at 0, I'm here. What is my initial velocity? Well, if I look over here at the graph, the first velocity is 10 meters per second, right? So I'm going to draw my first arrow, maybe fairly long here, at 10 meters per second. After 1 second, so if this is 1 second, I know my velocity is now just 5 meters per second, right? Okay, so my velocity has slowed down a little bit. So my velocity now is not nearly as long. It's only 5 meters per second. We do want to try to be specific with some of the information. And so what I mean by that is, what happens at 2 seconds? Well, what do we notice about the velocity at 2 seconds? Isn't the velocity at 2 seconds equal to 0? Okay, so at 2 seconds, that would be where this car turns around, right? That would be where this car stops and then turns around, or this particle, I guess I should say, stops and turns around. So at 2 seconds, that's our turning point. Can we figure out how far along the x-axis our turning point is? Well, yeah, we can do exactly like we just did on that last one, right? Can't I find the area underneath that curve here? So if I find the area underneath the curve, this will tell me how far I've gone from where I started. So we do want to try to reflect that on this axis if we can. So if I do that, well, this is just a triangle, right? So again, it's 1/2 base times height. So the area underneath that curve would be 1/2 my base, which is 2, times my height, which is 10. So obviously this just ends up being 10 meters. So again, what does that tell us? We don't turn around at 10 meters, but we turn around 10 meters from where we started. So I actually, right here, so maybe I'll fix this a little bit just to give myself some more space. But over here at 40 meters, that's where I turn around at. Okay, and I turn around at 2 seconds, right? So my first 2 bullets, my first 2 dots, my 0th second, I've got a fairly large velocity going off to the right. After 1 second, I still have a little bit of a velocity going off to the right. But at 2 seconds here, I shouldn't have any vector arrow at all, because what do we know about the particle at that moment? Right? At 2 seconds, the particle is at 0, so there is no vector on the dot. But then what about 3 seconds? Well, at 3 seconds, we know that it started to move back to the left, and at 3 seconds, its velocity would be back to maybe a -5, right? So the particle, the position, and again, if we were being actually very accurate, we could find out that this is 1 second over, 5 meters down, so it'd be about 2.5 meters back here. But that's where the particle will then be turning back around, so it's got a velocity of 5 meters per second there. After 4 seconds, it's going to have a velocity of -10 meters per second. And where would it be? Well, isn't it just as far from here to here as it is from here to here if I'm thinking in terms of area? So after 4 seconds, it should be right back to where it started, and again going about 10 meters per second, and so on and so forth, right? After the 5th second, it's going to be going even faster, and then after the 6th second, it's going to be even faster. Okay. So in doing this, and I probably won't quite finish this example in this first part, but in doing this, we've hopefully got a pretty good feel for part A. You do want to label all of the specifics on there, so what are the actual x values, and what are the velocities that it has. And we also answered part B, right? Where does the particle turn around at? It turns around 10 meters from where it started, so in this case it turns around at 40 meters. Right, so anyway, that's what we're looking at for this first one here, parts A and B. I will go ahead and pick up with part C in the next part of this wonderful video.